After the astounding success of my last video, I just had to make another one. This time I'm building a fridge. I was on Amazon, and I saw a deal for a mini fridge. I was about to buy it, but then I thought, why would I buy it if I can build a more expensive, uglier, shittier one myself? First thing I need is supplies. To cool the fridge, I want to use a Peltier module. This, when powered, gives off heat on one side and takes up heat, which makes it cold, on the other side. You might ask why it does that. This Peltier module is the core of the operation, but I need to power it somehow. To save money, I want to take the power supply out of an old computer and use that. And when I say old, I mean 1 GB of RAM old. I can't just plug the power supply in, I'll have to separate the wires apart by color first. Because, funny thing, each color gives off a different voltage. You know, the cables aren't there just to look bad. Yellow is 12 volts, orange is 3.3 volts, red is 6, and green is special. When green is connected and running, it turns on the rest of the colors. That's what's connected to the power button of your computer. But I can't just have those two things. That would be dumb. I need to insulate the precious cold that comes from the Peltier cooler. For that, I'm using some styrofoam insulation. I'm thinking about a box with 2 compartments, cold on one side, hot on exhaust on the other. Not much of a plan, but hey, it's not like you were planned. Now you understand how I wanted to build this. Next is the part where the plan goes to shit. See, I said in the plan part that I'm using a Peltier module, but dumb fuck old me looked at this and said, yeah, I can do that. No you can't! Are you dumb? Yes. And that's how this was born. A Peltier module smacked between 2 heatsinks and fans, way too weak to dissipate any of the heat from the cooler. It overheated and broke the Peltier the first time I tried it. Funny thing is, it also wasn't actually cheaper than the real Peltier module. Good job all around. Anyways, I bought the real thing and started building. First, I took apart the power supply and bunched the colors I wanted together and cut the ones I didn't need short. With some quick soldering, I have a 12-volt rail, a ground wire, the wire that goes from the cooler back to the power supply, and a green wire with its own small ground wire. Neat. Too bad it looks like, you know, a bomb. Now I built the chassis. I bought this shitty gray foam insulation for this, right? $20 for about the size of 2 mattresses. Let me tell you how hard this was to cut. Because this stuff is made out of miniature foam balls, you know, like styrofoam, it's impossible to get a straight cut. I went through a ton of it to get an okay result. Then, I painted the pieces. Not too much trouble there. To glue the foam pieces together, I used some adhesive specially made for foam because normal glue dissolves it. I went through a lot of it, and it worked well. At the same time, I also made the door for the fridge. I didn't want to muck around with an air-leaking side door, and instead settled for opening it from the top. I cut out a little piece from the top and attached a little edge frame thing that would rest on the ledge of the opening. A little paint, and a Jenga block as a handle, with some foam strips to make the insulation better, and it's looking adequate. Now, I cut a hole in the back of the fridge for the power supply, and 2 round ones on the side of the hot half to get the hot air out. All that's left was to solder the switch to the green and ground wires, install the cooler, and solder the cooler wires to the 12-volt ground wires. It worked! After around an hour of fixing air leaks. Neat. So, yeah, I'm done. But I still want to know, how does this fridge even work? Well, the cooler takes normal air and turns it into cold air and hot air. But like, how does the cooler work? Well, the way I understand it, a Peltier cooler is like a big long wire that's kind of smushed together, with two ceramic plates making it a sandwich. Wherever the wire touches the ceramic, there is a change in wire material. Now this is important, I think. The thing is, when electricity flows from one of these materials to another, the electrons, because, that's what electricity is made out of, jump to a different energy level. When an electron does this at a junction, the energy either used or given off to get to this different energy level is taken from or given to the environment. That's why one side gets cold, because, cold is the absence of heat, and the other side gets hot, as tons of electrons are doing this constantly. But you may ask, what, where, who, and why are the different energy levels? You're just a damn wire. How hard can it be for electricity to travel through it? But the thing is, isn't just a normal conductor like copper, it's a semiconductor. Now, what the hell is that? A semiconductor is made out of some sort of base material like carbon or silicon. This base material forms a lattice because each atom has 4 outer electrons and each atom connects to 4 other atoms. Makes sense, right? But this in itself does not conduct electricity. If you want to shove electrons through this, you just can't. There's nowhere for them to go. So, to fix this, they are given the Russian Olympian treatment. They are doped. Not with drugs, but with other atoms dispersed around the lattice, replacing some of the carbon or silicon. These other atoms aren't just normal atoms, but either have 5 outer electrons or 3 outer electrons. And as they try to fit into this lattice, something goes wrong. They either bind to 4 atoms and have 1 electron left over, for the atoms with 5 outer electrons, or bind to only 3 atoms and have a hole where the 4th electron would have gone, for the atoms with 3 outer electrons. So, what happens is that you have a base material with either a ton of holes or a lot of leftover electrons dispersed in it. Fun fact, if there's holes, it's called a p-type semiconductor, and if there's leftover electrons, it's called an n-type semiconductor. Fun. But, you might ask, how does this thing now conduct electricity? Well, for an n-type semiconductor, the one with leftover electrons, when you apply an electric field, like when you plug it in, electrons from the power source are pushing on the leftover electrons as if it's Black Friday on 2006 and the Nintendo Wii is on sale. And so, some other electrons on the other side are pushed away. A flowing stream of electrons follows, and that's electricity for you. For a p-type semiconductor, it's a bit weirder. Electrons coming from the power source jump across the holes in the material, kind of like the part in American Ninja Warrior, where the people have to jump across platforms to get to the other side. Here, the platforms are the electron holes. So, now you might say, okay, I understand how electrons move through the semiconductors, but how does any of this make the fridge cold? Well, I've got just the solution for you. The thing is, the electrons in the different types of semiconductors are in different energy levels. But wait a second. You know how electrons in an atom are not the same distance from the nucleus? Yeah, that's kind of important. Because the farther away an electron is from the core, the more energy it used to get there. This makes sense, because you need energy to pull a negative charge, the electron, away from the positive charge, the nucleus. Kind of like Earth, the space station, and gravity. Anyways, you can add energy to the electron. Say, like when you shine a light on it, you give it energy and it shows this new energy by going into a farther orbit. You can also cause this going into a farther orbit thing by somehow forcing this electron to go into the higher energy level instead of just giving it energy. In this case, the electron takes up energy from the environment in the form of heat, and thus cools the environment. You might see where this is going. The key thing here is that in an n-type semiconductor, the electrons flowing through are kept at a higher energy level than normal. Because to move through an n-type semiconductor, you need to be flexible, and being in a higher shell gives you this flexibility, since you're less strongly attached to the nucleus. But in a p-type semiconductor, electrons only move from valence shell to valence shell. Basically not much energy here. So, when you string up a ton of alternating p and n-type semiconductors, you force the electrons to jump up and down energy levels when they switch conductor types. As they do that, they either release or take up heat, depending on if they're moving down or up a shell. And if you smush the wire and have all of one type of junction on one side and all the other type on the other, you get a hot side and a cold side. Slap 2 ceramic plates on there, and boom! You got yourself a Peltier unit. And that's how my fridge works.